So guys, let's start with our first question. Focal length of a lens depends on. So on what factors focal length of the lens will depend on? We have four statements. Statement A says it depends on medium of the lens only. Statement B says it depends on medium of the surroundings only. Option C says, the statement C says that it depends on both the mediums, medium of the lens as well as the medium of surrounding. And statement D says it depends on the wavelength of the incident light. Now, statement D is looking out to be very colorful to me. So let me talk about this statement specifically. Actually, the focal length does depend on the wavelength of incident light. This statement is true. Now, I will tell you why it is true. Why does it depend on wavelength of the incident light? The reason is the refractive index depends on wavelength of the incident light. For different colors, we have different refractive index. Why does this happen? Because it is found out to be experimentally true. When we have white light in vacuum, all the colors travel with same speed. We know that. But as soon as the light enters some medium, then for different color, we have different velocity. For different color, we have different refractive index. Now, let me give you an example. For example, let's say white light is incident on a convex lens. And we can see as the light enters the lens, the splitting is happening. So for different lambda, we have different refractive index. That's why we are getting different focus. This is the focus for violet color and this is the focus for red color. Okay? Okay. Now, I just want you to remember one important point right over here. If lambda increases, then refractive index decreases. Okay? Okay. So for red color, lambda has the highest value and the refractive index of the red color is the least. Therefore, red color will suffer least bending and violet color will suffer most of the bending. Okay? Okay. So we got this concept and statement D is actually true. Now, what about the rest of the statement? Well, these statements deal with medium of the lens and medium of the surrounding. So let me take a specific color, let's say yellow color. We are doing the experiment only with one particular color, yellow color. For that yellow color, the refractive index are mu1 when the light is outside the lens and mu2 when the light is inside the lens. Okay? Okay. So these are the refractive index of the medium. Now, what is happening? We have to tell on what factor will the focal length of this lens will depend on. Will it depend on mu2 only? Will it depend on mu1 only? Or both mu2 and mu1? Well, if you remember lens maker's formula, the formula said it depends on mu2 and mu1 both. Actually, it depends on mu relative. And mu relative is mu2 divided by mu1. This is the lens maker's formula. We can see that 1 upon f is equals to, in brackets we have mu2 by mu1 minus 1 times, in brackets we have 1 upon r1 minus 1 upon r2. What is r1? What is r2? We can see these are the value of radius of curvature of both the surfaces. This is r1 and this is r2. Okay. We understand this formula. And you know, the focal length will depend on mu1 also and mu2 also. So let's mark option C. It says that statement C is true and statement D is true. Statement D said it depends on the wavelength of the incident light. We talked about that. It is true. And statement C says that medium consisting the lens as well as surrounding. Yes. So focal length depends on the refractive index of the lens as well as refractive index of the outside medium. Okay. So C, option C, C and D both. This is the right option for this question. Let's have a look at this amazing question. under what condition a concave lens can make real image? Oh, so we want to use a concave lens. This is a very beautiful concave lens. It is placed in vacuum. Now, can this lens really make a real image? We will find that out. So let's read the options. Option A says it can form a real image if we have real object placed between optical center O and focus f1. Now, let me tell you some important points. This lens will always make virtual image when we have a real object. No matter where we place the real object, it will always form virtual image if we have real object. Suppose we have the real object over here. Okay? So this is real object. By real object we mean light rays, incident light rays are diverging from this object. Okay? So these are the incident light rays. They were diverging. And after refraction we can see they are even more diverging. Oh, so this means these light rays after refraction will go like this. And if we extend them, they appear to meet at a particular point. At this point we will say virtual image is formed. If the light rays after refraction appear to diverge from a point, then at that point virtual image is formed. So in this case we have a real object, but the image is always virtual. Nice, nice. So option A is false. What about option B? Virtual object between optical center O and focus f1. Okay, let's talk about this virtual object. Suppose this is f1, our focus f1, and this is optical center O. Now let's take our object. So we will say that the incident light rays are appearing to meet at this particular point. So we will have a virtual object. So they appear to meet at this particular point. Very nice. So this is our virtual object. By object we mean the point at which incident light rays meet. In case they are appearing to converge at a particular point, then at that point we will call virtual object. That particular point is called virtual object. Okay? Okay. Now, let's see what will happen after this. After refraction, we can see these light rays actually meet at some point. So they were actually converging. Now they are still converging, but they were more converging before they encountered the lens. Now they are somewhat less converging, but they still converge. And when the light rays converge after refraction, we will get a real image. Okay? Okay. So we can form a real image when we have a virtual object. Now, something is really crucial over here. The location of the virtual object. Suppose I say the virtual object was at focus itself. Suppose these incident light rays were appearing to meet at focus itself. So let's say this is the location of focus. This is focus f1. Now what will happen after refraction? After refraction, these light rays will become parallel to each other. Nice. Now in this case, the image will be formed at infinity. We cannot say whether it is real or virtual. The image is formed at infinity because the light rays are parallel. So it is very important to see what is the location of our virtual object. If it is between the optical center and focus f1, then we will surely get the real image, right? Now let's see option B. Option B is true. What about option C? We have real object. For real object, we won't get a real image. So C is false. In option D also, we have a real object. So real object can never form a real image for this lens. So only option B is the right answer for this question. So guys, let's have a look at this beautiful question. A virtual, erect and magnified image is formed between f1 and 2f1 by a convex lens. So what do we have? We have a convex lens. and we want a virtual image out of this lens. So where should we place the object? The question says the position of the object should be. Where should we place the object to get virtual image? Now, let me tell you something. This is F1 and this is F2. If the object is beyond F1, then we will get a real image. If our real object is beyond F1, then we will get the real image. If our object is between F1 and optical center O, then we will get a virtual image. This is the concept. Just remember this. Before focus, we have a real image, and between F1 and optical center, we will get virtual image. Nice? Nice. Now, let's say this ray, which is parallel to the optical axis, we know it will pass through focus after refraction, and the ray which is passing through optical center will go as it is. So when we extend these rays, we can see they are meeting. They are appearing to meet at some point, and at this point we are getting a virtual image. This is virtual image, this is erect image, and this is also magnified image. Okay, so we should place the object between focus F1 and the optical center. So this is the concept for this question. Now let me tell you something interesting. Suppose what if we place our object at focus F1 itself? This is F2 and that was F1. So what if our object is at F1 itself? What will happen now? Now you will say after refraction, the rays will become parallel to each other. So if we have parallel light rays, if we even extend them, then these extension will meet at infinity. We will get a highly magnified virtual image. But this image is beyond 2f1. This image is beyond 2f1 for sure. Now suppose we want our image in between 2f1 and f1. Where should we place the object? You will say, well, let's suppose our object was at distance x from the optical center O. So this is the location of our object. This is our beautiful object at a distance x. And when the object was at distance x from the optical center, then we can see the image is formed at 2f1. Nice, nice. Now, if our object is between x and this position x and the optical center, let's say we will call it distance 0 from the optical center. If the object is between x and optical center, then we will get the image between 2f1 and f1. So this is the position of our image between 2f1 and f1, and object should be between x and optical center. We will call it 0, distance 0 from the optical center. So this is the condition. Now, can we find out x? You will say, yes, of course we can find out x. What if our object is beyond x? What if our object is very near focus f1? You will say, then we will get the virtual image, but that image will be beyond 2f1. So we need to find x. So let's try to find out x. How to find x? Well, we remember the lens formula. What is that formula? That formula was 1 upon v minus 1 upon u is equals to 1 upon f. This means v is nothing but u times f divided by u plus f. This is the shortcut. Now we have to be very careful. We have to place everything with their signs. The direction of incident light ray is taken as positive and the opposite direction is negative. So let's place all the values. Let's see what are we getting. What is v? What is v? V in this case is twice of focal length. This is 2f in the negative direction. So instead of v, I will just write minus 2f. And then we have u. What is u? U is minus x. Okay. And then we place f, and then we have minus x plus f. Good, good, good. So this is f. Now, when we solve it, we will get the value of x, and you can see this value of x is coming out to be 2f divided by 3. So, where should be our object? Our object should be between 2f by 3 and the optical center, so that our image is between 2f1 and f1. So we have solved this question finally. Now let's see the options, and we can see that option B is the most appropriate one to mark. So option B is the right answer for our question. Let's have a look at this wonderful question. For the diagram shown below, identify the correct statement regarding object AB, lens, and image A-B-. Assume that the size of the object and image is same. So what do we have over here? We have our object placed beyond F. So we have a convex lens and the object is placed beyond F. Whenever the object is placed beyond F in front of convex lens, we will get a real image, right? Right. So this is the real image of real object. Nice. Now these are the options. We have to pick the correct option. So let's read each and every option very carefully. Option A. Point B, its image B dash and optical center O of the lens are collinear. So this option says that these 3 points B, O and B dash are collinear. These 3 points are actually collinear. This is the first option. Are these 3 points collinear? Yes, they are. Why? Because any ray passing through optical center goes without any deviation. So this ray will go as it is. If the ray is emerging from point B, this ray will go as it is without any deviation. Okay, that's cool. So we can say the 3 points B, O and B dash are collinear. Amazing. This is point O. If you cannot see that, this is point O. Okay? Okay. Now we say that option A is perfectly true. What about option B? Option B says point B, its image B dash and optical center of the lens are non-collinear. Well, they were collinear. So option B is false. Option C, B dash is the point on the virtual image of the object. Well, B dash is the point on the real image of the object. This is the real image. Real images can be obtained on screen. So this is the point on real image, not the virtual image. Option C is false. Option D says that the image cannot be obtained on screen. Well, it can be obtained on the screen. So option D is also false. This was the real image. It can be obtained on screen. So only option A is the right answer for our question. So guys, let's see this awesome question. A concave lens has been placed in an optically rarer medium. How sweet! This is our concave lens. It is placed in optically rarer medium. Nice. Now the lens will behave like. So what is the behavior of this lens? Option A says converging lens. Option B says diverging lens. Option C says it will lose the property of lens. It will no longer be a lens. And option D says concave mirror. So weird. So what do you think is the behavior of this lens? Is it a converging lens or diverging lens? Well, we know the lens is placed in optically rarer medium. Now let's take the help of our imagination. Suppose this lens is made of glass. Now we want to place this lens in optically rarer medium. Can you imagine any optically rarer medium? Yes, we can. We can imagine air. Yes. Suppose we place this lens made of glass in air. So what would be the behavior of this lens? You will say diverging. Oh, when we have parallel rays of light and these light rays are diverging after refraction from the lens, then we conclude our lens behaved like a diverging lens. Exactly. So this lens will behave like a diverging lens when it is placed in optically rarer medium. Now note, for these diverging lens, focus is on this side. Okay, and according to sign convention, we take the direction of incident light rays as positive and the opposite direction as negative. So focus is always negative. So focus is negative for diverging lens. In case focus comes out to be positive, then we will have converging lens. Otherwise, if focus is negative, we have diverging lens. Just remember that. Now suppose there would have been a more complicated question other than this question, then how could you find out whether the lens is behaving as a converging lens or diverging lens? Well, in that case, if you are not able to use this imagination which we used to solve our question, if you are not able to use that, you can always use a formula. Let me show you an important formula. The formula is lens maker's formula. Okay. Now let's try to apply this formula. The formula is 1 by f is equals to mu2 upon mu1 minus 1 times 1 upon r1 minus 1 upon r2. You will ask, what is this mu2? What is this mu1? What is this r2? What is this r1? Well, I will show you. Mu2 is the refractive index of the material of this lens, and mu1 is the refractive index of the outside medium. Okay. And we can see R1 is the radius of curvature of this awesome cool surface. This is R1. Got it? Let's say the value of R1 is A. Okay. And what is this R2? What is R2? R2 is the radius of curvature of the other surface. This is R2. Got it? This is R2. Now let's call it B. Let's call this length as B. Awesome. Now let's really apply this formula and find out whether we are getting the positive value of f or negative value of f. So let's take the incident light rays. These are the incident light rays, and you can see this direction in which the light rays are traveling is positive and the opposite direction is negative. So cool. So let's apply this formula. Let's find whether f is positive or negative. So let's quickly do that. 1 upon f. This is equal to now mu2 by mu1 minus 1. This thing is greater than 0. Why? Because mu2 is greater than mu1 given in our question. In our question, they said mu2 was greater than mu1. The object was placed in optically rarer medium. That's why mu2 is greater than mu1. So we get something as positive. And then the second term, is it positive or negative? Well, let's see. 1 upon r1. Now r1 you can see is negative. Right over here it is negative. Why? Because it is on negative side. So we will write 1 upon minus a. Okay. So 1 upon minus a. And then we have minus 1 upon r2. R2, is it positive or negative? It is positive. We can see it is plus b. So we will write plus b over here. Now the second term, as you can carefully see, is coming out to be negative. So 1 upon f has some positive term and then it has some negative term. Okay. So 1 upon f comes out to be negative. So f is negative. If f is negative, then we have a diverging lens. So these light rays will diverge after refraction, and we can see if we extend them, they will appear to meet at this focus which is on the negative side. So we have diverging lens. So this is how we can solve this question. Now suppose the outside medium was optically denser medium than the material of the lens. So if mu1 is greater than mu2, then what? Then what will happen? Then reverse will happen. Then you can see the first term, mu2 by mu1 minus 1, this is less than 1. So when we try to find out 1 upon f, we will see the first term as negative term and the second term is also negative term. So f is positive. And if f is positive, then we will have a converging lens. Okay. So it depends on the outside medium and the material of the lens also, whether it is behaving as a converging lens or diverging lens. So cool. So in our question, mu2 was greater than mu1. So we don't have this case. We only have this case where the focus is negative and our lens behaved like a diverging lens. So good. Now let's mark option B, diverging lens, as the right answer for our question.